Okay, so let's do some examples to see how procedurally we go and do these limits as x goes to infinity. All right, so let's take this first one here, a, and say the limit as x approaches infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. Okay, so what we're seeing is that if we actually did plug in infinity, so we don't literally plug in infinity because it's not a number, but we can think about plugging in infinity and see what's going to happen. Think about plugging in really big numbers. So if we put in infinity in the top, well, if we put in really big numbers into 3x squared, they're going to get even bigger. And even though we'd subtract off something that's going to infinity, the x squared dominates. So this whole numerator is going to go off to infinity. And the same thing on the bottom is going to go off to infinity. So we're dealing with an infinity over infinity situation, which is an indeterminate situation. And so we are going to have to find a way around that. So in this case, we're not going to try and factor. We actually like the way we have it now. So what we're going to do is we're going to divide through, by the highest power in the denominator. Okay, so the highest power in the denominator here is x squared. So I'm actually going to divide both the numerator and denominator by x squared. So I'd have the limit as x approaches infinity, and I'll just do 3x squared minus x minus 2, put it over x squared, and 5x squared plus 4x plus 1, put it over x squared. Okay? And then what I'm going to do is actually distribute that, to each of the terms. So, for instance, where I have the 3x squared over x squared, that would reduce to just 3. And then the minus x over x squared would be minus 1 over x from there. And then the minus 2 over x squared. So that would be the numerator. In the denominator, I would get 5 plus 4 over x after reducing plus 1 over x squared. Okay, so that's actually a much better situation now, because now I have things that I can actually do the limit for. So take a look. What's the limit of 3 as x approaches infinity? Well, that's a constant. It still goes to 3. Minus, what's 1 over x? The limit of 1 over x as x goes to infinity? That's what we just talked about in one of those important rules. If x is going to infinity, then 1 over x is going to 0. 2 over x squared, the denominator would also be blowing up here. This goes to 0. 5 in the denominator would go to 5. 4 over x would go to 0. 1 over x squared would go to 0. And so all together we have a numerator that would be going to 3 minus 0 minus 0, or in other words 3, and a denominator that would be going to 5 plus 0 plus 0, 5. And there's our answer. 3/5 is our limit. Now this is a very formal way of doing this, and in a bit I'll show you a little bit of a shortcut that we can use quite often on these in these nice situations. But for now, let's look at this formal approach. All right, so let's look at B now. Let's do the same thing. We notice that it would be going to infinity over infinity, so we have to do more. So we'll again divide through by the highest power in the denominator, which this time is going to be x cubed. So I'm going to take 2x squared plus 1 over x cubed, and I'm going to take 3x cubed plus x over x cubed. And let's see what I get. On the numerator, I'm going to get 2 plus 1 over x cubed. And then the denominator, oh, I'm sorry, I made a mistake there. Go back. I'm going to get 2 over x plus 1 over x cubed. Because in that first one, that was 2x over x cubed. So it's still leaving x in the denominator. Okay. So now in the denominator of the original whole thing, I get 3 plus 1 over x squared. Okay, and this is all going to infinity. All right, so now take my individual pieces. 2 over x as x goes to infinity goes to 0. 1 over x cubed goes to 0. 3 goes to 3, and 1 over x squared goes to 0. So I get 0 over 3, but that's just 0. There we go. Let's take a look at this one in C. All right, still, we're starting with an infinity over infinity situation because both the numerator and denominator are going to go to infinity. So I'll use my idea of dividing through by the highest power in the denominator, which is x squared. So x to the fourth plus x squared over x squared, all over x squared plus 1 over x squared. All right, and so simplifying the numerator, I would get x to the fourth over x squared is x squared plus 1 over 1 plus 1 over x squared. Okay, so let's now take this all to infinity. But notice x squared, as I go off to infinity, this is still going to go to infinity because it's still just x squared. 1 will go off to 1, 1 will go off to 1, and 1 over x squared will go off to 0. Now, the whole thing then, I've got a numerator that's going off to infinity and the denominator that's going to 1. So this means this whole fraction is just going to go off to infinity. And in fact, it's positive infinity because when I put in positive numbers towards infinity into x squared, they were still positive. So I have positive infinity, and there's nothing else turning it negative. We'll see more of those. So that answer is infinity. Again, limit doesn't exist, but we say infinity. So there is a real shortcut here because we could have noticed something, all right? Basically, all of these examples here are a comparison between a polynomial in the numerator and a polynomial in the denominator of some power. And so basically, as x goes to infinity, we're seeing this battle between a numerator and denominator because a numerator going off to infinity wants to make the fraction go off to infinity. The denominator going to infinity wants to make the fraction go to 0. So they're having an opposite effect, and we're trying to see who wins. Well, in this first one that we were looking at, you have the same power on the top and the bottom. And when I say power or degree of the numerator denominator, the highest power in each, they're both x squareds. So in that battle between them, they basically tie. And what's left over is simply the coefficients. So I could see actually that if you have the highest power the same in the numerator and denominator, you just take the ratio of the leading coefficients, the coefficients of those powers, and that's how it could have gone directly to 3/5. In the second one here, the denominator has the higher power, x cubed, versus the x squared in the numerator. So the denominator wins, and a denominator going off to infinity is going to bring the whole fraction to 0. I could have gone directly there. In this one, we have the numerator has the higher power, the x to the fourth compared to the x squared in the denominator. That means that it's going to, and the numerator is going to end up winning and taking this off to n infinity. So I will have to do a little more analysis in these because it's going to depend on all the signs of whether I'm going to positive infinity, the sign, the even or odd nature of the exponent, and the signs of the leading term in the denominator as well. So we'll see more of that. But this is going to go to n infinity. In this case, it did go to positive infinity. So I can summarize that down here. If you have a degree of the numerator equal to the degree of the denominator, the limit as x goes to infinity, or negative infinity, in fact, is going to equal to the ratio of the coefficients of the leading terms. If the degree of the numerator is less than the degree of the denominator, so the denominator has the bigger degree, the denominator wins and takes it to 0. If the degree of the numerator is bigger than the degree of the denominator, then the numerator wins, and it's going to be either plus or minus infinity, depending on all the signs in the problem. All right, so we can use that moving forward. We can always divide through by the highest power in the denominator, and that'll still show us, it'll confirm for us, but we can use this shortcut if we like. And we will.